Okay, this is the exam review for midterm number 2. As a reminder, this will be chapters 4, 5, and 6. And as you'll see from the review today, the distribution of topics is not exactly even, but there will be some of all of that. So there's, as we go through, about 5 questions on chapter 4. I think there's about 6 or so on chapter 5, and the rest are on chapter 6. It's a little bit heavily weighted towards chapter 6, but there'll be some of everything. Before I get into the questions, the problems that are on the review, I want to do a quick overview of something that could come up on the test for some of you. Again, it's a question bank, so you might not see any of this, but I didn't really cover it in detail in class, so I just want to make sure that we're clear on it. And that would be the shapes of hybrid orbitals. So back in chapter 2, we talked about the shapes of atomic orbitals. You have the spherical s orbitals, the figure 8 or dumbbell-shaped p orbitals, and then the d orbitals that are mostly like four-leaf clovers. Hybrid orbitals also have shapes, and we're not going to really get into too nitty-gritty of the difference between sp, sp2, and sp3, but they all basically have the same shape. So they're going to be 2 lobes, kind of like a p orbital, but the 2 lobes are going to be unequal in size. So something like that. And it's almost like, again, a superposition of an s and a p orbital. So there's going to be, if you're asked to describe the shape, 2 lobes, but they're unequal in size for any individual sp, sp2, sp3 orbital. Now there's going to be, as I said, subtle differences. So the lobes will be a little bit closer in size in sp and a little bit more distorted in sp3, but we're not going to get into that level of detail. You should just know that any of these sp, sp2, sp3 hybrid orbitals have this basic shape. And then the other thing we could ask you about is the arrangement of those hybrid orbitals. So if you have a set of them, so if it's sp orbitals, you'd have 2 of them, sp2 you'd have 3, sp3 you'd have 4 of them. How do they arrange themselves then as a set? And that's again going to correspond to the electron group arrangement or molecular shape that they correlate with. So for sp orbitals, you would have 2 identical orbitals at a 180-degree angle, and that gives you a linear geometry for sp. So you'd have 2 identical orbitals facing the opposite direction, essentially. As we recall, sp2 correlates with the trigonal planar electron group arrangement. So a set of sp2 hybrid orbitals is going to have, again, 3 identical orbitals, this time arranged in a trigonal plane, 120 degrees apart. All right, and again, that's the entire set of sp2s. That's 3, so you can see there's 3 of them here, 3 yellow blobs. Each one of those represents an sp2 orbital. And then for sp3, the corresponding electron group arrangement is tetrahedral, so those 4 orbitals would arrange themselves in a tetrahedral shape, pointing in those directions at 109.5 degree angles, and that's going to be your sp3 set of orbitals. So those are kinds of the 2 things we can ask you about shapes of hybrid orbitals, either the shape of an individual orbital or when you arrange a set of them around your central atom, how do those look? And that again just correlates directly with the shape that they correspond to. So any questions on that? Just something I just wanted to quickly clarify. Yes?
Why are the lobes unequal?
The lobes aren't equal because you can almost think about it as, let's just do sp as the simplest one. You're taking an s orbital, which is spherical, and you're blending it with a p orbital that has 2 lobes of opposite phase that are equal to each other. So when you combine these 2 together, imagine putting this on top of this, you're going to partially cancel out the shaded lobe because it's out of phase with the s orbital, and then this lobe is going to reinforce because you have in phase there, so you'd get something like this, where that'd be a little bit reinforced because you're adding the 2 phases that are like, and then the other half, they're opposite in phase, and so it partially cancels out, and that's how they end up unequal to each other. Okay, any other questions? All right, so with that, let's get into the problems then. So the first problem is going to deal with the concept of VSEPR, which is closely related to hybridization that we just talked about. So here we want to do the electron group arrangement and molecular geometry, respectively, for the hypothetical anion trifluoroselenate, SEF3-. Okay, so what we're going to do for this is anytime you're dealing with molecular geometry or hybridization, you need to have a good Lewis structure first to be able to answer the question. So we'll review the process for drawing a Lewis structure, which was technically covered on chapter 3, but it again could be important for some of the things you need to do on this exam. So for a Lewis structure, we need to count valence electrons first. So this anion has selenium and fluorine, so we need to figure out their valence electrons. Remember that we go to the periodic table for that. and we use the group number to figure out the number of valence electrons that each atom brings in. So selenium is in group 6, so it would have 6 valence electrons. Fluorine is in group 7, so each fluorine is going to bring 7 valence electrons.
Wait, selenium is in which one? Yeah, like,
It's group 6, so it's right there, SE.
yeah. Right.
Yep, so SE is there, group 6. Fluorine is there, group
So
7.
that means like group 6 will mean like 6 valence electrons?
Yeah, so for those main group elements, the ones that are labeled with A in this numbering system, 1A, 2A, 3A, 4A, and so on, the group number tells you directly how many valence electrons any atom would have that's in that column.
Right.
So that's how we count valence electrons. And so we'll have 1 selenium, which is 6 electrons,
1 helium is 6 electrons.
and then 3 fluorines are 7 each. Then what we can't forget about is if you have an overall charge, which we do here, a minus charge, you have to add additional electrons for that. So 1 more electron to go in for the negative charge, and that gives you a total of 28. Right?
Yes.
The vast majority of Lewis structures have even numbers of electrons, obviously. All right, so then we're going to draw the structure, and again, there's, you probably have your own internalized method for doing this by now, but the step-by-step approach would be to start with single bonds to the outer atoms,
Right.
so selenium and 3 fluorines,
Yes.
and then we're going to complete the octet of the outer atoms next. So unless it's hydrogen, which only would form 1 bond, you need to add additional electrons to get up to a total of 8. So we're going to add 6 non-bonding electrons to each fluorine. We now have a total of 8 around each fluorine. 2 from the bond, 6 additional non-bonding electrons. So at this point, we've used 8, 16, 24. 3 complete octets is 24 electrons, but our entire structure should have 28. So whatever's left goes on the central atom as a non-bonding electron. Now, as we talked about in this whole thing is negative charge. As we talked about in chapter 3, there are potentially some additional analyses you can do to decide if you need double bonds and things like that. But for VSEPR, for predicting the geometry or for predicting the hybridization, you don't really need to worry about that. This one would not have any double bonds, but nonetheless, we can stop here as long as we have the correct arrangement of electron groups around the central atom. That's what's most important. So then if we want to classify this structure using the AXE notation, as we often do, this one would be AX3. There's 3 atoms bonded to the central atom, and there's the 2 lone pairs, so it's going to be AX3E2.
Yes.
And then what's going to determine then the electron group arrangement. So this is a 2-part question. We're looking for electron group arrangement and molecular geometry. Those are 2 different things. Sometimes they're the same for a molecule, but they're 2 different ways of classifying it. Electron group arrangement is determined by the total number of electron groups. So the number of electron groups in this molecule, that's the total number of atoms plus the number of lone pairs on the central atom, 3 plus 2, which is 5. All right, so if it has 5 electron groups, then the electron group arrangement will always be what? Trigonal something. Yes, trigonal bipyramidal.
Right.
And that's any combination of 5 electron groups. So whether it was, X5E0 or X4E1 or X3E2 like we have here, any combination of 5 will be a trigonal bipyramidal electron group arrangement. So if we are confident in that, we can get rid of some of the answer choices already because they have the wrong electron group arrangement. But for C and D, we need to figure out what the correct molecular geometry is. Is it T-shaped or trigonal planar? So what we do is we draw out the trigonal bipyramidal arrangement, which can be drawn as just a triangle with a flagpole up and down, five points. And then in a trigonal bipyramidal electron group arrangement, whatever lone pairs we have, in this case 2 of them, have to go onto the triangular part. So we put 2 there. That leaves a fluorine there, a fluorine there, and a fluorine there.
Yes.
And even though this is drawn sideways from how you would think about it, that's a T-shape. So imagine
Right.
putting that on its side. So that's going to be a T-shaped geometry. So AX3E2 corresponds to the T-shaped geometry. Trigonal planar would be AX3E0, so that's not going to be the correct one. So that's going to be our answer there. C, trigonal bipyramidal electron group arrangement. When there's 5 electron groups, that's what it's going to be. And then if it's 2 lone pairs as part of that, T-shape would be the correct geometry.
Right. So trig bipyramidal, that's, and T-shaped.
Yes, that's correct.
So in short terms, how do we get it? So that's T-shaped there, right?
The T-shape will be the molecular geometry. That's just going to be the shape that the atoms themselves occupy when you sort of ignore the lone pairs. So
Right.
it's a sideways T as I've drawn it here, but
Yes.
it's a T rotated at 90 degrees. You'll see a T shape, and that's what we call it for that categorization.
Yes. AX3
Well, how
to
much is the fourth? Fluorine?
It's only 3 fluorines. It's F3.
Oh.
So if there was a fourth fluorine, it would go. You'd have only one lone pair on the triangle, and the fourth one would be also on the triangle. But in this case, there's only 3 of them. Yeah.
So,
All right.
Right.
Okay.
So,
We good on that? All right.
right.
All right. The next question is going to be also related to VSEPR, which is a question about dipole moments. So which of the following molecules have a non-zero dipole moment? Now, again, in these problems, there's more than one way of wording things, but they kind of mean the same. So non-zero dipole moment means that it would be polar. So something that's non-polar has 0 or no dipole moment. Something that's non-zero is going to be polar. And we don't really have a good way of ranking polarity either. So really all the questions you have to do about polarity are just going to ask you in some way to differentiate, is it polar or is it non-polar? That's really all it's going to come down to. So even if we ask you what's the most polar molecule, it would have to be just the one that is polar, because we don't have a good way of saying which molecule is more polar than the others in most cases for for more complicated structures like these. All right, so if we want to find the molecule that is polar, we have to remember that there is a sort of a correlation between the the VSEPR geometry and the polarity, and there's some patterns that are helpful to follow. So I did give a whole table in the notes when we cover this that could be helpful to look at. But first of all, in pretty much all the structures we'll have you evaluate, and this is true for these ones here, all of the molecules just have one type of outer atom. So it's NF3, only fluorine. BF, these are all fluorides actually. But nonetheless, for each individual answer choice, they all just have one type of outer atom. So that means there is a pretty simple relationship between the geometry and the polarity that we don't have to really think about it much more in depth than that. So in general, what we'll find is that if we have an AXM E0 structure, which means we have no lone pairs on the center atom, that's going to be nonpolar no matter what the total number of electron groups is. So if it's AX3, or if it's AX2, AX3, AX4, AX5, AX6, if there's no lone pairs on the center atom, it's going to be nonpolar, as long as all the outer atoms are the same.
Right.
And then the other one that we will commonly encounter is if there's one lone pair on the center atom, no matter how many X's there are, no matter what those X's are themselves, that will be polar. Now there's a few options, and we'll come across a couple of these here that have 2 or 3 lone pairs on the center atom, and for those, some of them are polar, some of them are nonpolar. So you need to either remember which one is which or think about the structure and try to determine whether those individual bond dipole moments would or would not cancel each other out. And we'll talk about that as we come across them today. But let's go through the answer choices then and determine their polarity. So I'm not going to go through all the details of drawing the Lewis structure like we did last time, but what we would produce for all of these for NF3 is that it's going to be AX3E, so it's going to be a trigonal pyramidal. Yes, question?
So non-zero dipole moment means polar?
Yes.
Okay.
Yeah, so if it has a dipole moment, that means it's polar. If it does not have a dipole moment, that means it's nonpolar.
Right.
Okay, so then we're going to do, for the first one, NF3, it's going to be AX3E. As we said, anything with one lone pair, E or just E1, is going to be polar.
Yes.
So we don't necessarily have to draw the structure or think about it in any more detail than that. If we go to BF3, which is the next answer choice, we would come up with AX3E0, or just AX3, so there's no lone pairs on the center atom. All of those structures with no lone pairs would be nonpolar. And then the next two we get to are going to be the ones that are a little bit more complicated. So we're going to have to think a little bit more about their structure because they have more than one lone pair. So that makes, there's either possibility. So for xenon difluoride, I think this is the only common molecule, at least neutral molecule, that would have this classification. It's AX2E3. All right, so we need to think about whether it's going to be polar or nonpolar, and for this it's going to be helpful to draw out the structure. So if it's AX2E3, it has 5 total electron groups, and as we said in the last problem, that means it's going to be trigonal bipyramidal in terms of the electron group arrangement. And then however many of the lone pairs we have always go on the triangular part of the trigonal bipyramid. So we have 3, they're going to all occupy the corners of the triangle, and that leaves the fluorines here and there. So what do we call this geometry? Well, there's no more, the top of the t is gone.
Linear?
So it's going to be linear if it's only, so remember when we have AX2 with whatever many lone pairs, it's either going to be linear or bent. Those are the only two options for 3 atoms, AX2, E, whatever. So it's going to be linear or bent, and this one's linear because the 2 fluorines occupy these 2 apical positions exactly opposite each other. So that makes it linear. And any linear molecule, again, if the 2 atoms are the same that are bonded to the central atom, any linear molecule would be nonpolar. So there's other linear geometries as well, like AX2, that would also be nonpolar. Which would be in that case
You said
E0.
anything that's linear is non-polar?
Yep, as long as the 2 atoms that are bonded to the central atom are the same,
Yes.
which they are here. They're both fluorine.
Yeah.
Okay, so any linear molecule in this classification would be nonpolar, so that one's nonpolar. And then the last answer choice, or no, so there's 2 more to go. Another one that we have to think a little bit about is xenon tetrafluoride. This one comes out to AX4E2. Again, with 2 lone pairs, you have more than one possibility. So for AX4E2, what we end up with is 6 electron groups, which is octahedral. So it's a square now with one coming up above and below the square. And for AX4E2, the lone pairs need to be as far away from each other as possible. So they go 180 degrees apart, and that leaves atoms on the squares or the corners of the square. So it's called a square planar geometry. And this one's not as obvious, but by a similar argument as the linear geometry, what we have is dipoles canceling each other out. You have a dipole going towards this fluorine, which cancels out with that dipole. You have a dipole going towards that fluorine, which cancels out with the one that's opposite of it. So it's going to be also nonpolar. All the bond dipoles cancel out in this square planar geometry. So that was probably the one that's the least obvious of these. But it's going to be nonpolar when it's AX4E2, where you now have 2 sets of basically superimposed linear units that cancel each other out in terms of their dipole. And then finally, SF4, what we would come up with this one is AX4E. Now, the name of this geometry is one that people often forget for some reason, even though it's kind of the most unique name. It's called seesaw, but nonetheless, anything that has 1 lone pair in the central atom, as we said, will definitely be polar. So all those possibilities are polar once we figure out there's 1 lone pair in the central atom. So we're looking for the polar ones, and so that's going to be NF3 and SF4. So that would be number 1 and number 5, which is choice C again.
Yes.
Okay, so for these types of problems, you do have to be able to get at least the AXE notation, at least think a little bit about the shape, and that's going to then relate to whether it's polar or not. So there are some other obvious ones to look for. So like if you just have a diatomic that's the same atom, like O2, that of course is nonpolar, it's 2 of the same atom. But for a lot of these, and the ones in this problem, you have to also draw out the whole shape and consider it. So any questions on polarity, or this problem in particular? All right, if not, I'll move straight on to the next one. And then this one deals with hybridization. So same molecule that we had done before, SEF3-. So most of the problems on hybridization on the exam will ask you to do something just like this, just determining the hybridization of an atom in a molecule. And so to do that, it also comes down then to the electron group arrangement. Each hybridization possibility that we have correlates with one of the possible numbers for electron group arrangement, 2 through 6 being the total number we can have. So for SCF3, we did the Lewis structure of this in problem 1, so I don't have to do it again. You likely won't be that lucky on your exam, but I just wanted to save some time and give the same compound again. What we came up with for that one was AX3E2. And for hybridization, again, what always matters is just the total number of electron groups, not how many X's and how many E's you have, but the total.
The steric number.
Or the steric number, as I call it in class.
5.
Your book doesn't use steric number, so I'm trying to wean myself off of that term, but I still like it. So steric number is 5 because there's 5 total electron groups.
Right.
And the steric number is going to then determine how many orbitals need to hybridize. So if we have a steric number of 5, we need to hybridize 5 orbitals to generate that trigonal bipyramidal arrangement.
Right.
So the orbitals that we have available for hybridization are an s orbital, we have 3 p orbitals, and up to 2 d orbitals, which can sometimes come into play. And so those are the possible orbitals. We need to hybridize 5 of them, so we just take the first 5. 1, 2, 3, 4, 5.
That would give us sp3d.
Correct. So that will give us sp3d hybridization. All right, so we have sp3d hybridization, which would be answer choice C once again. So I guess I'm in love with letter C today. But nonetheless, that's don't let that freak you out in the exam. Remember, your exams are random, so we're not going to like try to drive you into a psychological fit by giving you all the same answers. That's just not possible with the way the exams are set up. So just pick whatever you think the right answer is and don't worry about things like that. Question over here.
How do you get the steric number again?
So steric number is total number of electron groups. When you write it out in AXE notation, it's the sum of the subscripts, so 3 plus 2. It's another way of saying total number of electron groups.
E stands for lone pairs. Like the number by E is like how much lone pairs there.
Yeah, so in the AXE notation, E is the number of lone pairs on the central atom specifically.
Right.
All right, so that's the steric number of 5. So when you're doing hybridization, there's only 5 possibilities, and it all is determined by that steric number, or again, what is more commonly referred to as just the total number of electron groups. So the possibilities are 2, 3, 4, 5, and 6, and the hybridization that corresponds to each of those is hybridized 2 orbitals would be sp, 3 orbitals would be sp2, 4 orbitals sp3, the one we just saw was sp3d, and the highest possibility is 6 orbitals sp3d2.
Right.
Sometimes you'll see the d written first, so d sp3 is the same as sp3d, and d2 sp3 is the same as sp3d2. Don't be concerned about that, but you're going to get those possible values for hybridization depending on how many electron groups you have. Let me check on the recording because these videos are long and I just don't want to have any problems with this. Okay, we're good. All right, any questions on hybridization? Yeah.
Where do you get the AX3D2?
So that was from problem 1. So we did that Lewis structure up here, which you may have not been here for that. So when you draw the Lewis structure, you're going to figure out how many atoms are bonded to the central atom, which you can get from the formula, and then how many lone pairs. That's going to be the E part of that notation. So we had the Lewis structure already, so I just quickly skipped to that part. But if you don't have the Lewis structure, you need to do that to get the number of electron groups that are present.
And the S and the 3Ps and 2Ds.
So those are the orbitals that are available for hybridization in any molecule. And that's the order that they would sort of hybridize in. So it's a valence s orbital. Usually, in this case, it would be 3s, I think, because it's selenium, or 4s. But anyway, whatever valence s orbital you have, 3 valence p orbitals, and then for some of the higher order structures like this, we also invoke d orbitals, which it's a little bit of a lie, but it's a lie that helps us understand the truth. So I guess it's okay. But nonetheless, that's how we would classify it as sp3d in this case. Okay. Any other questions? All right, let's keep going. All right, the next 2 problems are going to deal with molecular orbital theory. So this will be true on your exam as well. This mock exam is not real exam questions, but it is the same order of topics that you'll see. So questions 4 and 5 on the exam will deal with molecular orbital theory. And the first one of those, like we have here, will deal with either sort of conceptual ideas related to that or possibly like simpler molecular orbital diagrams like H2, which just has a sigma and a sigma star. And then the second of those, as we'll see, will deal with the more complicated diagram that involves S and P orbitals. So there's kind of 2 flavors of this that you'll see. So this one is more of a conceptual question, and it asks, according to molecular orbital theory, which of the following will increase the bond order in a diatomic molecule? So remember that in molecular orbital theory, what we do is we have an ordering of molecular orbitals from lowest to highest energy. Some of them are bonding, some of them are anti-bonding, and we add electrons to those, and we count how many electrons are in each of those types of orbitals, bonding versus anti-bonding. And from that, we get a bond order calculation that's fairly simple, which is 1/2, and then what we take is the number of bonding electrons, that's the number of electrons in bonding orbitals, minus the number of anti-bonding electrons. All right, so that's the calculation for bond order, which we're kind of considering here in a more conceptual level. So let's think of what happens if we add electrons to each of these types of orbitals. So if we start adding electrons by to the whole count, if we add electrons to bonding orbitals, what we'll see is that is going to increase the bond order because we're making this part of the formula bigger. So anytime we add electrons to bonding orbitals, that's going to increase the bond order, make the bond stronger. And then if we add electrons to anti-bonding orbitals, we'll see the opposite will happen mathematically. Because if we add to anti-bonding orbitals, we're making this number bigger, which we're subtracting from the total, and so that's going to shrink the bond order and make it smaller or make the bond weaker, as we would say.
Wonderful.
All right, so here what we're looking for is the things that will increase the bond order. So adding electrons to bonding orbitals will increase the bond order, so that one is true.
Yes.
If we add electrons to an anti-bonding orbital, that'll decrease it, so it's not that one. And then what happens if we remove electrons? Well, removing electrons is the opposite. If we remove from a bonding orbital, this number gets smaller, and that will decrease bond order. But if we remove electrons from an anti-bonding orbital, that decreases this number, which then increases the overall bond order.
Right.
So those two, A and D, will both increase the bond order of a molecule. Adding electrons to a bonding orbital will strengthen the bond, or taking them away from the anti-bonding orbital would also strengthen the bond. So the correct answer for this is E. Two of those would increase the bond order. All right, any questions on that? Yep.
So they use the word diatomic molecule, but it doesn't really matter if it's diatomic or not.
It doesn't matter if it's diatomic, but that diatomic is the only type of molecule that we will deal with in the context of molecular orbital theory. So diatomic, remember, just means X2, some atom bonded to itself. Or you could do heteronuclear ones like, XY, two different. But molecular orbital theory is a lot more complicated for other shapes, but it still does work pretty much the same way, yeah. In terms of this context, yeah. All right, anything else? Okay, so on to number 5, which is the last of the chapter 4 questions. So here we're asking you, according to molecular orbital theory, what is the bond order and number of unpaired electrons for what's called the dioxygenyl cation? I did not spell that right. It should be cation. O2 plus.
Right.
Okay, so for these types of problems, we're telling you explicitly to use molecular orbital theory. But if we give you a diatomic molecule and ask something about bond order, number of unpaired electrons, that's what you should immediately think about in this part of the course is molecular orbital theory, because that's the most accurate way of predicting these things. So for this, what we need to do is we need to draw the correct diagram. So for molecular orbital theory, there's 2 possible diagrams, but what we need to do is order the orbitals correctly. So at the bottom is always going to be sigma and sigma star 2s. So this is oxygen, which has 2s and 2p valence electrons. So we're going to use those orbitals in our molecular orbital diagram. So the 2s orbitals combine to make a bonding and anti-bonding sigma orbital derived from 2s. And then in the 2p, it's more complicated. You can make sigma and pi orbitals. In oxygen, the sigma comes first at the bonding level. So sigma 2p comes before pi 2p.
Yes. Yes.
And then the anti-bonding orbitals are at the top, and those always occur in the same order.
Right.
Pi star, and then sigma star.
Okay.
So again, these 2 orbitals here are the 2 that can switch. So if you're in the first half of the p block, boron, carbon, nitrogen, these 2 would flip their order. Now that's not going to be important for bond order, but if you're trying to find number of unpaired electrons, that does play in many cases. So you need to make sure that these are in the correct order, especially if we ask you about number of unpaired electrons, which we do here. So that's going to be the correct order of those. And then from there, whatever question you're asking, you just need to populate this with the correct number of electrons, and then go from that point. So what we need is the correct number of electrons for O2 plus. All right, so for O2 plus, again, we use the periodic table to tell us valence electrons. Oxygen is the first group 6 element, so it would have 6 valence electrons for each oxygen atom. So O2 would have 12, 2 times 6.
Yeah.
But then we're going to remove 1 because we have a positive charge. So in total, this is going to have 11 valence electrons. And if you're trying to draw a Lewis structure of something with odd number of valence electrons, it gets pretty tricky at times, but for molecular orbital theory, it's no problem. So we have an odd number of valence electrons. And what we're going to do then is we're going to populate the diagram with these 11 valence electrons going from lowest energy to highest energy orbital. So we need to put 11 in here. Each orbital can hold 2 electrons, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that last electron goes up here into pi star. So the configuration for this, which we don't really need for this problem, if we were asked to write it out, would be sigma 2s2, sigma star 2s2, so those are both filled. Sigma 2p is filled with 2 electrons. Pi 2p is filled with 4 electrons. There's 2 of those degenerate orbitals. And then our pi star has 1 electron in it. So that's the total configuration, which we don't really need to worry about for this problem, but that would be what it is. But the 2 things that it's asking are bond order and number of unpaired electrons. So bond order is going to be again, that same formula we just talked about. It's 1/2, and then you're going to take the number of bonding electrons and subtract the number of antibonding electrons. So we have 11 total electrons in this diagram. We need to figure out how many are in bonding orbitals, how many are in antibonding orbitals. So the bonding orbitals are the ones that don't have a star next to them. So that's going to be these two, 4, 6, 8. So we have 8 electrons in bonding orbitals. Sigma 2s, sigma 2p, and pi 2p has 8 electrons total. So that's going to be our bonding electrons. Then we're going to subtract from that the antibonding. So if 8 of them are bonding, that means 3 should be antibonding. That's going to be these two there, sigma star 2s, and that one up there, which is in pi star.
So
Yes?
which ones are the bonding and which ones are the anti-bonding?
So bonding orbitals are ones that they're lower in energy than the atomic orbitals, and in terms of how they're labeled, they don't have a star next to them. So it's going to be sigma 2s, sigma 2p, and pi 2p are your bonding orbitals. The ones that have a star next to them, sigma star 2s, pi star, and sigma star up here, those are all of your antibonding orbitals.
Okay, got it.
And so it's going to be 1/2 times 8 minus 3, which is 2.5. So that's our bond order. And then the number of unpaired electrons, we have all the first 10 electrons are paired, 2, 4, 6, 8, 10. But this lone electron up here is unpaired, so it's going to be 1 unpaired electron. Now there are some shortcuts that you can use to help yourself a little bit in problems like this, and they would come into play in this one in particular. So if you have an odd number of electrons like we do here, 2 things are going to be true. First of all, the bond order has to be fractional. It has to be something 0.5. You can't have a whole number bond order if you have an odd number of electrons because of this equation here. The subtraction of those is always going to be odd. And then second of all, the number of unpaired electrons, if it's an odd number, is going to have to be 1. So if it's 9 electrons, 11 electrons, 13 electrons, whatever the case is, if it's odd, one of those will be unpaired, and that's always going to be the case. If you have an even number of electrons, then it can be either 0 or 2, so you have to draw it out and look at the diagram. But for anything with an odd number of electrons, it's going to be 1 unpaired, and the bond order has to be fractional, something 0.5. So make sure that both of those are true if you're dealing with anything that has an odd number. Okay? So any questions on that? Yeah.
Why do you split the pi 2p into 2?
So the reason that pi 2p is split into 2 is that it's 2 degenerate pi orbitals. And so those are going to be formed by, so if you want to sort of draw it out, you have your molecule here. So those are going to be formed by overlap of p orbitals that are sort of perpendicular to the bond. And they're sort of delocalized above and below the bond like that. And there's going to be one of those that's in this direction, and there's going to be another one that's 90 degrees apart, which will be pointing out towards you as I've drawn it. So there's basically 2 identical orbitals that are just rotated 90 degrees to each other, and they're both at the same energy. So that's why they show up here together at the same level, and that's why they would get filled one at a time, just like we would for degenerate atomic orbitals. And the other thing about that is keep in mind that you have to have however many atomic orbitals you have the same number of molecular orbitals. So we are mixing together 8 atomic orbitals, a 2s and 3 2p orbitals from both oxygens for a total of 8. So that gives us 8 molecular orbitals, and 4 of those, a set of pi and a set of pi star, would be degenerate at those respective levels. Yep.
Aren't there cases where the sigma 2p and the pi 2p flip?
Yes, so the reason that I put a red box around these two here is because there are cases where these would be opposite of each other, where the pi 2p comes below sigma 2p, and that's going to be for the first half of the p block. So it would be, boron, carbon, nitrogen, or anything else in those same columns. You'd expect those to have that inverted order for the bonding p orbitals. So that's the one thing that can flip. It won't affect your bond order calculation, and in the case of an odd number of electrons, it'll always be 1 unpaired no matter what. But in other cases, you do need to have that correct to make sure you get the right number of unpaired electrons. All right, anything else? Okay. So we're going to move on to Chapter 5 now. And the first topic in Chapter 5 was the definition of atomic mass. So when you read atomic mass off the periodic table, what exactly does that refer to? Well, that's, as we said, a weighted average of all the isotope masses. So that's the concept that's going to be at play in this. And there's going to be a problem on the exam that requires you to use that idea. So here we have a hypothetical element, TT, which just by coincidence has my initials, nothing to that. And it has an atomic mass of 132.2145. So that would be, if that element appeared in the periodic table, that's the number you would read off the bottom. So remember, in the periodic table, this number here that's below the element symbol, that's the atomic mass, and again, that's an average atomic mass of all the isotopes. So that would be that number there. And we're telling you here that it has two stable isotopes, 131 and 134, with these respective masses. Now, in problems like this, they could be set up in two ways. So sometimes we'll give you the exact isotope masses like we did here. Other times we won't. In that case, you would just assume that the mass is equal to the mass number. So you can see they're close. So the one that has a mass number of 131 has an atomic mass that's pretty close to 131, but a little bit off from that, and same with 134. It's not exactly 134. So if we don't give you the exact isotope masses, you would just assume that the isotope masses are 131 and 134. That's the best you can do. But in this case, we gave you the exact ones, so those are numbers you're going to want to use. And in any problem like this, no matter what we're asking you to solve for, so what we're asking you to solve for here is the percent abundance of the 134 isotope. So that's one possibility, but we could also ask you to solve for other things as well. But they all revolve around the definition of atomic mass, which is that the atomic mass, again, the number that appears on the periodic table, is going to be equal to the weighted average, which is the abundance, the fractional abundance of each isotope. In this case, it's 131 and 134. And then you're going to multiply by the mass of that isotope, plus the abundance of the second isotope, times its mass. So really whatever we ask you to do about atomic mass in this problem on the exam is going to have something related to this idea here, this definition of atomic mass, the mathematical definition in particular. Now that said, you could have more than two isotopes, in which case this equation would keep extending, but we're not going to be too cruel to you. It probably wouldn't be any more than three on an exam. And for problems like this, we would limit it to two when the abundances are unknown. So in this problem here, we were trying to find this abundance here, but we don't know either of them. So we have basically our given information is the atomic mass. We gave that as 132.2145. And the masses of the two isotopes are given. So let's keep track of what we already know. But what we don't know is either of the abundances, and we're trying to find one of those two. So we'll call these our unknowns, x and y. Those are unknowns. And this equation has two unknowns, so we need a second one to relate x and y, and that's always going to be that the sum of the fractional abundances will equal 1. So these, as a percentage, the sum would equal 100. As fractions, the sum equals 1. And that's going to be the other part that we're going to use. So what we're going to do is we're solving for y. That's the abundance of 134. That's what we're looking for. So we're going to rearrange this as x equals 1 minus y. And we're going to substitute that in to there. All right, so we can combine these two equations as such. So we're going to start writing out the numbers now. So the atomic mass, which is given as 132.2145, that's equal to the abundance of the 131 isotope, which is 1 minus y, times its mass, which is 130.9856. And if you'll forgive me, I'll leave units out of this equation just so we can solve for it numerically first. And then we're going to add to that the abundance of the second isotope, which is y, multiplied by, let me use a dot instead of a time sign so it looks like x, which is the abundance of the second one, times its mass, which is given as 133.9767. So those are the numbers from the problem. All right, so we're going to solve for y, which I'm not going to go through all the algebra here, but y is our fractional abundance of the 134 isotope, which should come out to 0.4109. But what we're looking for in the problem is percent abundance. So make sure you always read the problem carefully. Are we looking for a fractional abundance or a percent abundance? Percent is always going to be fraction times 100. So the percent would be that number, 0.4109, multiplied by 100 to convert it to a percentage, which is 41.09%. So that means if you have a naturally occurring sample of this fake element, 41.09% of the atoms will have the mass number of 134, and the rest would be the 131 isotope. Okay, so that's how we do it. It's really just this one equation here, and just figure out what you're trying to solve for, essentially. And sometimes you have to combine it with a second equation if both of your abundances are unknown as they were here. Okay, questions? All right. All right, the next few problems are going to deal with, we're now into chapter 5 if you're trying to orient yourself with where we are in the progress of this exam. And the next few are going to deal with relationships involving moles and then progressing into stoichiometry. So this first problem here is a typical mole conversion. So we want to know how many moles of sodium ions are present in 65.65 grams of sodium phosphate. So if we're doing a mass to mole calculation, we know that we're going to need the molar mass at some point to do that. So to get the molar mass, we need the formula, and then we need to find out the molar mass by adding up the atomic masses in the formula. So if we have sodium phosphate, sodium from the periodic table is in group 1. So sodium would be a +1 cation in any ionic compound. So we have to get the formula of this compound correct, or else we're not going to be able to do this. So sodium is a +1 cation. And then we need to remember our polyatomics from the last section. So phosphate is PO4 3-, so make sure we remember that. And then to get the correct formula, the dummy way to do it is just to take the charges and cross them down to the other one and make them the subscripts. So that comes out to Na3PO4. So that's going to be the correct formula for sodium phosphate. So we know the mass of sodium phosphate we have. We're doing a calculation that involves finding the number of moles, so we need its molar mass, or molecular weight as it's sometimes abbreviated. So the molecular weight or molar mass of this compound is just going to be the sum of the atomic masses, 3 sodiums, 1 phosphorus, 4 oxygens. So the atomic masses, again, come from the periodic table. If you've done as many stoichiometry problems as I have, you'll start remembering them whether you want to or not. But sodium is 22.99, phosphorus is 30.97, and oxygen is 16. So those are going to be the 3 atomic masses we need, sodium, phosphorus, oxygen. And the sum of all of those in the formula gives us the molar mass for this compound. So we have 3 sodiums in the compound, so we're going to multiply its atomic mass by 3, so 22.99 is the atomic mass of sodium. We have 1 phosphorus in the formula, and its atomic mass from the periodic table is 30.97. And then we have 4 oxygens, which are 16. So the molar mass of this compound is 163.94 grams per mole. Now you'll see on the exam, depending on how involved the problem is, sometimes we'll give you molar masses, but in a lot of cases we won't, so you need to make sure you know how to calculate it quickly by just, again, adding up the atomic masses. It's pretty straightforward. So then from there we have all the information we need to do the calculation that we're interested in. We're looking for the moles of sodium ions, moles of Na+ in this sample. We're given the mass, that's what we start with, 65.65 grams of sodium phosphate, so that's Na3PO4. And then from there we can convert this into the number of moles by using the molar mass that we just found. So we want grams of sodium phosphate to cancel, and we want to find moles. All right, so we're going to put this number 163.94 in the denominator. That's the number of grams of sodium phosphate in 1 mole. So grams cancel out. Now this is the part where a lot of people would stop the problem. They would just divide these two and call it a day. But what we're looking for, again, is moles of sodium ions, Na+, in the formula, not the total moles of Na3PO4. So for that, if we want to find the number of moles of an individual ion or an individual atom in the formula, we need to look at the formula. And the formula, again, has 3 sodiums in it. So the last conversion we have to do, these formulas can be interpreted in terms of individual atoms or in terms of moles. So when we read a formula Na3PO4, that could mean that one formula unit has 3 sodium atoms, 1 phosphorus, and 4 oxygen atoms, or it can be interpreted as 1 mole of sodium phosphate has 3 moles of sodium, 1 mole of phosphorus, and 4 moles of oxygen. They work the same way. So in this case, what we're going to do is we want moles of sodium phosphate to cancel, and we want to find out how many moles of sodium ions there are. And as we said, the formula has 3 in it, so there's 3 moles of sodium ions for every mole of sodium phosphate. So that last step there is critical, which a lot of people tend to forget when they do problems like this. And so we get 1.201 moles of sodium. And this being a numerical question in Blackboard, you would just enter the number, so don't try to enter units. Just the numbers as we would specify, and that's the number that you would put in, 1.201. Okay, so you have to make sure we remember that last step, that we're accounting now for the number of sodium ions in the formula to get that last piece of it done correctly. All right, so any questions on that? Yep.
Do you know an example whenever like the subscript isn't going to be the mole of the element?
I don't think so. So whenever you have the subscript in a chemical formula, if you're trying to find a relationship between the moles of the compound and the moles of one of those elements that are in the formula, or an entire ion in the case of phosphate if you're treating it as a polyatomic, the subscripts would tell you how many moles of that element or how many moles of that ion are present per mole of the compound. I think that's always going to be true.
Okay.
Anything else? All right. On to number 8. All right, so number 8 is we learned a few different approaches for determining unknown chemical formulas, or empirical formulas as it asks us to do here, which is related. And the one way we found was to use mass percentages to do that. So there's a few variations on this problem, but if we're given mass percentages, that's going to be one common approach. So what we have here is a compound called catechol. It has 65.4% carbon, 5.49% hydrogen, and 29.1% oxygen by mass. And we want to know what the empirical formula is. So in any problem like this, what we basically want to find is the mole ratio of the elements, because the mole ratio of the elements tells us then the chemical, or more specifically the empirical formula of the compound. Empirical formula is the lowest whole number ratio of all the elements in the compound. And so that's what we can get from mass percent. So for mass percent, what we're going to do is we're going to assume that we have 100 grams of compound, because however much compound we have, the mole ratio is going to be the same. That's the law of definite composition that we learned about back in chapter 1. And so if we assume 100 grams of compound, then the mass percentages tell us how many grams of each element there are in that 100 grams of compound. So if we have 100 grams of this compound, we'd have 65.4 grams of carbon, 5.49 grams of hydrogen, and 29.1 grams of oxygen. And we know now, having gone through chapter 5, how to convert grams of anything into moles of anything by using the molar mass, or in this case the atomic mass if it's just a simple element. So we're going to find the moles of each element now by using its atomic mass. So we assume that we have 65.4 grams of carbon. And then for each of these we just need their atomic masses to convert grams into moles. Right? Because the atomic mass from the periodic table again is the number of grams of that element per mole. And so for carbon it's going to be 12.01, hydrogen is 1.01, and oxygen is 16. So those are the three that we need. All right, so we're going to do carbon first. 1 mole of carbon has a mass of 12.01 grams. That's the atomic mass of carbon. So that comes out to 5.45 moles of carbon. For hydrogen, we looked up its atomic mass quickly before as well. That's going to be 1.008. So the mass percent for hydrogen is 5.49. So this 100 gram sample would have 5.49 grams of hydrogen. And then 1 mole of hydrogen has a mass of 1.008 grams. Again, that's the atomic mass from the periodic table. So that comes out to about the same number, 5.44. And then finally for oxygen, what we get is the mass percent for oxygen is 29.1. So in 29.1 grams of oxygen, we use the atomic mass of 16, dividing by that. This comes out to 1.82 moles of oxygen. All right, so then we have these numbers here, but what we want for an empirical formula is a smallest whole number ratio. So the way that we do that is we start with the actual numbers that we have, but this would not be a standard way of writing an empirical formula because all the numbers are decimals. But then what we do is we divide all of them by whatever the smallest of those molar amounts is. So 1.82 is the smallest number that we have for oxygen, so we divide all of those by 1.82. That's going to normalize that smallest one to 1. And in this case, we get whole numbers directly. So when we do that, we get C3H3O. And maybe one of those two, carbon or hydrogen, might be like 3.0001 or 2.999, but that's close enough. If it's really close to a whole number, we can just round. And we get C3H3O for that, which matches up with choice A. Now, in this problem, we just asked for the empirical formula, so we stop there. If we ask for the molecular formula could be any whole number multiple of this empirical formula. So it could be C6H6O2, or it could be C9H9O3 or something like that. So if we want the molecular formula, you need additional information. You would need the molar mass of the compound as well, comparing it to the empirical mass to figure out what factor you multiply this by to go from empirical to molecular formula. But here we just stop at empirical formula. That's all we can get with this information, and choice A is the correct one. Okay, so choice C could be the correct molecular formula, and in fact I think it is for this compound, but nonetheless we don't know the information to get the molecular formula, so we would only choose A, which is the correct empirical formula. Right, any questions on that? Yeah, in the back?
So let's say we're talking about molecular. So let's say they give us 500 grams of C3H3O or whatever empirical formula is, right?
Yeah.
So like how would you go about finding the molecular formula?
So the way you'd find the molecular formula is if they'd have to give you the molar mass of the compound as well. So for catechol, it would be, let's see, 72 plus 6 is 78 plus 32 is 110, if I did that math right in my head. So basically what we would say is that the molar mass, I hope I did that right, is 110 grams per mole. So with this information and with the empirical formula, you can find out the molecular formula. So what you do is you also need to find the empirical mass, which is the mass that comes out from the empirical formula. So that's going to be 36 for carbon, plus 3 is 39, plus 16 is 55. So the empirical mass would be 55 about, when we sum up the atomic masses from the empirical formula. So then when we divide those, 110 divided by 55, molar mass divided by empirical mass, we get 2. And so what that means is that our molecular formula would be 2 times the empirical formula, or C6H6O2, which would be one of the answer choices, but not the correct one for empirical formula. So catechol would be, if I'm thinking about the structure correct in my head, it would be C6H6O2. Yes. Yeah, so if you don't have the molar mass, you cannot figure out what the molecular formula is exactly. Yeah, in this case you multiply by 2, because when you divide the molar mass by the empirical mass, that's a factor of 2, which means that the molecular formula is 2 times the empirical formula. Yes. Yep. So that would have to be given to you. So that's the actual molar mass of catechol. And that's in the formula would be C6H6O2, but you wouldn't know that ahead of time. You would just know this number that would give you 110, and then that would be provided to you, and then you compare that number to the empirical mass to figure out what factor the empirical formula needs to be multiplied by.
So if we don't have the molar mass, we can't find it.
Correct. If you don't have the molar mass, you cannot find the molecular formula. I mean, the only exception would be, if you have answer choices where only one of them is the correct empirical formula, then you know that that's also the correct molecular formula. Like, if we ask for which molecular formula is consistent with this, and only one of them had the correct empirical, that would be your answer choice. But yeah, if you're trying to select a bunch of different options that all have the same empirical formula, you need to know the molar mass to figure out which one of those is correct.
And that would be good.
Yeah, so if you need it, it'll be given to you. Yep. All right, anything else? All right, 40% there. Let's go to number 9. So number 9 is balancing a chemical equation. So that's going to come up in a few possible contexts on this exam. So we learned about how to just balance equations in general in Chapter 5. We learned about in Chapter 6 a few different categories of aqueous reactions that you should know how to balance. And then, of course, the last 2 problems, as we'll get to, are going to be balancing redox equations, which has its own approach that we need to follow. So there's a few different ways that can come up. This would just be sort of a standard one where we describe a chemical reaction to you, and you need to produce the equation and get the correct coefficients. So barium phosphate reacts with sulfuric acid to form barium sulfate and phosphoric acid. We want to know what is the coefficient on sulfuric acid when the equation is balanced with the smallest possible whole number coefficients. So to do this, we need to have the correct molecular or chemical formulas for all the compounds that are involved. So barium phosphate. Now we told you the symbol for barium is Ba. So if we go to the periodic table, we see that Ba is here in group 2, so it's an alkali earth metal. And then phosphate was the polyatomic anion that we just had in a previous problem. So barium is going to form a +2 cation, just like all the other elements in this column. So in an ionic compound, barium would be +2. And then phosphate, as we said before, is PO4 3-. So that's the formula for the first compound. So the 2 plus and 3 minus anions combine, and the correct formula would be Ba3 and then PO4 taken twice. So barium phosphate would have that formula to balance the charge of the 2 plus cation and 3 minus anion. And then the other reactant is going to be sulfuric acid. So sulfuric acid is the acid that comes from sulfate, which is SO4 2-. And the acid for that would be H2SO4. So remember that for acids, however many negative charges we have in the anion, we use hydrogen to balance out that negative charge. So it's H2SO4. So those are the two reactants, barium phosphate. Let me get a little bit of space in case I need to put a coefficient in there. So barium phosphate and sulfuric acid. And then we're told that the products are barium sulfate and phosphoric acid. So it's kind of like an ion exchange reaction, but one of the ions is hydrogen, H+. So barium sulfate would be the barium 2 plus cation with the sulfate SO4 2- anion. So the formula for that would just be BaSO4. And then finally we have phosphoric acid. So phosphate is PO4 3-. So the acid of that would be H3PO4. Okay, so those are reactants and products. We do need to remember how to take the name of a compound and turn it into a formula for those few categories we talked about, so that if you have to do something like this, you can get the formulas correct. Because without the correct formulas, we can't balance it and get the coefficients correct either. So now we have to start balancing, and typically we can do it by sort of one ion at a time for ionic compounds that are primarily involved in these. So barium, we have 3 bariums, so we'll put a coefficient of 3 there. We now have 3 sulfates, 3SO4, so we'll put a coefficient of 3 there. We have 2 phosphates, so then a coefficient of 2 can go there. So whatever order you want to do that in, those should be the coefficients that you come up with. So it's going to be, let's check everything that's balanced. So we have 3 bariums, 2 phosphates, 6 hydrogens, 2 times 3 is also 6, 3 sulfates. So for most reactions that involve acids, ionic compounds, the coefficients are fairly small. But here we have some, and what we're looking for is the coefficient on sulfuric acid when we're balancing with the smallest possible whole number. So sulfuric acid is this one here. The coefficient is 3, so the answer choice that's correct is choice C. All right, so that's a pretty typical balancing equation problem where we sort of describe it to you. You have to write out the chemical formulas and then provide the coefficients to make sure it's balanced on both sides. Yep.
Barium and sulfate. Aren't these both atoms going outside line, right? So it should be like sulfate.
Well, there's only one sulfate, because for barium sulfate, the cation is barium 2 plus, and the anion is SO4 2-. So they cancel each other out, so you just need one of each. So you would, if you use sort of the dummy approach I shouldn't say dummy approach, it's not a bad approach, but if you use this approach of crossing those charges and making them the subscripts, you get Ba2 SO4 2. But remember, for ionic compounds, we always want to write them as the smallest ratio. So instead of writing it as 2 and 2, you write it as just one of each, BaSO4. And it wouldn't be wrong to put the SO4 in parentheses if you wanted to. I mean, that's not going to matter if you do that. It's fine. But you don't have to if it's just one of those ions that's in the formula. All right, any other questions? All right, so the next two are going to be stoichiometry, or what I think is one of my favorite topics in this class, but we may not agree on all those things. But anyway, the first one, so on the exam, you're going to have, as this is laid out, 2 regular stoichiometry problems. That would be, just typically mass to mass or mole to mole type stoichiometry problems. And one of those 2 is going to be a more straightforward one like this one, where you just basically one of the reagents is in excess, so you just have to start the calculation. The other one, as we'll see in the next problem, involves determining a limiting reactant. And there's some variations, like we might ask you about percent yield and things like that, so those can come into in either of those cases. But basically, one stoichiometry problem will require you to determine a limiting reactant. But for both of them, you should at least think about whether that's necessary or not. So in this problem here, we have 3.25 grams of butane, which is burned or combusted in the presence of oxygen to form carbon dioxide and water. And we need to know the mass of CO2 that forms in grams when that happens. So in this problem, we're explicitly telling you that one of the reactants is in excess O2, so we don't have to worry about figuring out which reactant is the limiting reactant, because whatever one is not in excess is going to be the limiting reactant by definition. So in this case, we know already that butanes are limiting reactants. We don't have to go through any steps of figuring that out or worrying about whether we're choosing the right limiting reactant in this case, because we're only telling you the amount for one of the two reactants, and we're explicitly telling you as additional bonus that the other one is in excess. But we do need to start with a balanced chemical equation. So it's going to be butane, which is C4H10. And then we should be familiar with combustion reactions by now, although they will always be described to you if you need to produce one. But in a combustion reaction as it's described to us, it's going to be some compound, usually of carbon, hydrogen, or maybe oxygen as well in the compound. You're going to burn it in the presence of O2, so O2 is the other reactant. And then the two products of a combustion reaction are always going to be carbon dioxide and water. So it's described to you in that way here, but that's again a pretty standard reaction type that we should be getting familiar with just by doing it a bunch of times. So those are reactions and products, and then from there we can start balancing. So balancing a combustion reaction, what you're going to want to start with is carbon and hydrogen, because carbon and hydrogen typically only appear once on each side of the equation. So carbon is here in the reactant, there's 4 of them. So that means we need to have a 4 in front of CO2 to balance carbon. Hydrogen, there's 10 of them in the reactant. So we need to have 10 on the product side, which means H2O takes a 5. And then from there, we'll balance oxygen last. So right now, on the right side of the equation, we have 4 times 2 is 8, plus 5 is 13 oxygens. And so we need 13 on the left. So if we have O2, we need 6.5 or 13 over 2 to have a total of 13 oxygens in the formula, or in the reaction. Okay, so 13 over half times 2 is 13, and that's the same as the number of oxygen on the right side. Now, you could stop here and use this form of the equation. There's nothing wrong with having fractional coefficients. Usually, if we ask you to balance an equation, we'll specify whole numbers, and you should assume that if we don't specify it. But for a stoichiometry problem, it doesn't really matter as long as the ratios are correct, which they already are. But I don't like to deal with fractions in general, so the more standard way of balancing this would be to double all the coefficients to get rid of that over 2 fraction. So then what we'd come up with is 2 C4H10. Remember, we have to double every single coefficient, not just the one that's a fraction. 13 O2s, and then 8 CO2 and 10 water. So this is the more standard way of balancing it, where all the coefficients are whole numbers. But for a stoichiometry problem, you don't have to balance it this way. You could have stopped after the first step as well. But once we have a balanced equation, and once we know that butane has to be our limiting reactant, because it's the only one that we're told about, then we can go ahead and do the calculations. So we're looking for mass of carbon dioxide, and this is going to be a typical mass-to-mass stoichiometry problem. We have mass of a reactant, and we're trying to calculate the mass of one of the products. So when we do that, we write out what we're looking for, which is mass of carbon dioxide, and we start with the mass that we're given, which is 3.25 grams of C4H10. The first step in any stoichiometry problem is to convert to moles. So if we start with mass, we're going to use molar mass to convert in moles, as we've done already today. So the molar mass is given as 58.14. So there's 58.14 grams of C4H10 in 1 mole, and we're going to divide by that number so that grams cancel out. And now we have moles of C4H10. Once we have moles of one reactant, we can convert to moles of any other reactant or product in the reaction by using the mole ratio. So we're looking for CO2, so we're going to use those coefficients. We want to find moles of CO2, and we want to moles of C4H10 cancel. And from either of the balanced equations that we have, I'll use the second one since it's all whole numbers. The coefficient in front of CO2 is 8, so that means that 8 moles of CO2 form for every 2 moles of C4H10 that react. So it's going to be 8 over 2 or 4 over 1 if you had used the first form of the equation. So that gives us some moles of CO2. So you have to also, whenever you're doing questions like this, that's why I like to write out exactly what I'm looking for so I know when to stop. So here we are looking for mass of CO2 in grams, so we can't stop here because this is just moles. So the last step is going to be to convert moles back into grams. So we want moles of CO2 to cancel, and we want grams of CO2 as the result. So that's going to again be the molar mass, which was given as 44.02. So there's 44.02 grams of CO2 in 1 mole. That cancels out moles, gets us to the unit we're looking for, which is grams. So we stop there and multiply across, and we get 9.84 grams of CO2. This is a numerical question, so you would just enter in the number 9.84. All right, so that's a classic mass-to-mass stoichiometry problem. You have to make sure you have a balanced equation to start with, and then from there it's going to be a very similar set of steps. Now there are variations, so don't think you're always going to have to do it this way. Sometimes we'll give you moles and you'll be asked to find moles of something else, or sometimes we'll give you grams and you'll find moles of product. I mean, there's a lot of variations, you know, in whether we're asking you for different quantities of substance and usually mass or moles. But you know, the key step again is going to be getting the mole ratios right, and then other conversion factors that involve converting moles into other units as necessary. Okay, any questions? Yeah.
So because you multiply by 2 at the top, you put 2 at the bottom for moles of C4H10?
Yeah, so I'm using this form of the equation here, where it's going to be 8 for CO2 and 2 for C4H10. Because when you double the coefficients to get rid of a fraction, you have to double every single coefficient, not just the one that's doubling, that has the fraction. So that's why we got to these numbers here. So yeah, it'd be 8 over 2 as it's written in that form. Yeah?
Could you use the other?
Yeah. Yeah, so you can use the first equation. This is also balanced. In that case, you'd get 4 over 1, which is the same as 8 over 2 mathematically. It's just that if you're doing anything with oxygen with that one, you'd have a fractional coefficient, and you know it's a little bit easier to mess that up, but it would still work. All right, any other questions? Okay, halfway there. How are we doing on time? Oh dear, we're doing badly on time. Okay, so number 11. Another stoichiometry problem. What is the theoretical yield of gold chloride in the reaction shown below? So here we gave you the equation, so we don't have to balance it. Well, it's already provided for us. If 29.6 grams of gold are combined with 10.5 grams of HOCl in the presence of excess HCl. So we are told that this is an excess. One of the ratios is excess. But we want to know how much of this product is formed here. Now in this problem here, we're giving you the masses of 2 reactants, gold and HOCl. So anytime you have amounts for 2 or more reactants, you have to figure out which one the limiting reactant is. There's no way around that, or else you're not going to be able to do the problem. So as I said, I do like to find that out ahead of time. Just find the limiting reactant first instead of doing a bunch of calculations. So in this situation, what we're going to do is we're going to find the moles of each reactant that we're given. So the moles of gold and the moles of HOCl. So for gold, we have 29.6. And I didn't give you the molar mass of that, but that's an element, so we're just going to use the number from the periodic table. I won't flip back to it, but it's going to be 196.97. So we're going to convert grams to moles for both reactants. So that's 0.150. But then what we need to figure out limiting reactant is not just the number of moles of that substance, but what I term as the stoichiometric ratio, where we take that number of moles and divide it by the coefficient in the balanced equation. All right, so this 1.150, and the coefficient in the balanced equation is 2 in front of AU, so that's going to be 0.075. All right, so that's going to be our coefficient for gold. Then we're going to do the same thing for the other reactant where we're given the exact amount of it, which is HOCl. All right, so we have 10.5 grams of that substance. And we're going to divide by its given molar mass of 52.46. And that number, is that 0.2? Yeah, it should be 0.2, right? We're very close to that.
Yeah, it is 0.2.
Okay. I didn't write that number down, but I think that's right. All right, so we have 0.200 moles of that. Now again, we might be tempted to say, oh, there's more moles of this. That must be in excess. But remember, it's not determined just by number of moles. It's determined by the stoichiometric ratio. So when we calculate R for this, we take that number and divide by its coefficient, which is 3 in the balanced equation, and we get 0.067, which is a little bit smaller than 0.075. So this is going to be our limiting reactant because the stoichiometric ratio is smaller. So then once we know that that's the limiting reactant, any calculation we're going to do in this problem is going to start with this substance here. So what we're looking for is the theoretical yield of gold chloride. So that's going to be the mass of gold chloride that can form using stoichiometry. And we're going to start with the amount of our limiting reactant. So we could start with this mass, but we already calculated moles. So let's just start there to save a step. So we have 0.200 moles of HOCl. And then from the balance equation, we can convert into moles of gold chloride. So we want moles of HOCl to cancel, and we want to find moles of gold 3 chloride. So that's going to be 2, and that's going to be 3. And then we told you that the molar mass of gold 3 chloride was 303.32, so to get back into grams of that substance, which is what we're looking for, we use that molar mass, grams per mole. And that leaves us with 40.4 grams. Which I guess I should give you it to 2 decimal places, but I don't have it to 2 decimal places, but that's fine. Blackboard's not that picky. All right, so whatever your number is to 2 decimal places will be what you'd answer, but to the correct number of digits it'd be 40.4. And again, you have to use the correct limiting reactant to get that number, otherwise you get a number that's too big and it would not be the correct answer. All right, any questions? All right, since we're a little bit behind, let's keep moving on. All right, the next question, we're on to chapter 6 now, and the first of these is going to be a conceptual question about electrolyte solutions, aqueous solutions. So we're looking for which of the following aqueous solutions would not conduct electricity at all. So whenever we're talking about the electrical conductivity of a solution, that's its electrolyte properties. And there's essentially 3 categories: strong electrolyte, weak electrolyte, and non-electrolyte. So a strong electrolyte solution is one where when you dissolve the compound in water, it separates completely into its ions. So that's either going to be a soluble ionic compound. Any ionic compound that dissolves in water would be a strong electrolyte, or a strong acid. Now, technically, strong bases are in this category too, but strong bases are just ionic compounds of a special type, so it doesn't really need to be a separate category. But anything that separates into ions when you dissolve it in water would be a strong electrolyte. And then a weak electrolyte is one where when you dissolve it in water, it's going to produce some ions, but you're not going to have all of the molecules or all the formulas separating into ions. So it'll just sort of partially separate. And the categories of compounds that would be in there are going to be weak acids or weak bases. All right, and both of these solutions would conduct electricity. Any electrolyte solution conducts electricity. All else being equal, a strong electrolyte will conduct electricity better because there's more ions in the solution than a weak electrolyte, but both will conduct electricity. And then the other kind is a non-electrolyte, which is one where you don't have any ions separating when you dissolve the compound in water. So that would be any covalent compound that's not an acid or a base. And these ones do not conduct electricity. All right, so pretty much any other covalent compound except for acids and bases would be fall into this category. So they don't produce any ions and they don't conduct electricity. So for these lists of substances here, we just need to classify what type of substance it is and then decide if it's a strong, weak, or non-electrolyte. So HNO3 is a strong acid. So nitric acid is one of our strong acids, so that's going to make a strong electrolyte solution. Calcium chloride is an ionic compound and it is soluble, so that would be a soluble ionic compound. So both of these are strong electrolytes. Now if we go to this one here, CH3CH2OH, we don't need to know too much details about the names of these compounds, but anything that ends in just OH by itself is going to be what's called an alcohol, and all of those are going to be soluble in water, but they're not going to be electrolytes. They're just regular old covalent compounds. So this is going to be just a covalent compound here. Something as a little bit of an aside, if the formula of a compound ends with OH, it's going to be an alcohol and it's going to be just a regular covalent compound. If it ends in OH, 2 oxygens and then H, that's going to be a weak acid, kind of like acetic acid, the one that we already have seen a lot. All right, so there's a little bit of a distinction there to keep straight when you're looking at formulas of compounds, but if it just ends with OH by itself, not OOH, that's going to be an alcohol, which is just a regular covalent compound, so this would be a non-electrolyte. KOH is a soluble ionic compound, and so that would be a strong electrolyte. And then H3PO4 is an acid, and it's one of our weak acids, so it would be a weak electrolyte. So of these answer choices, the only one that wouldn't conduct electricity at all is the one that's just a regular covalent compound, non-ionizable, which is going to be choice C, CH3CHOH, which is called ethanol, the active ingredient in adult beverages. So that's going to be a regular covalent compound, which would mean it's a non-electrolyte solution. Yes?
What's the chemical code for acetic acid?
So acetic acid, which is the simplest of these OOH acids, and probably the only one you'll see, is CH3COOH, or it's sometimes written as HC3H2O2, but this form is a little bit more indicative of the type of compound that is, which means if it ends in COOH or OOH in particular, that makes it a weak acid for our purposes. All right, anything else? All right, on to number 13. All right, so now we're going to deal with the concept of molarity in a couple of different problems. So here we have a solution with 25.65 grams of calcium perchlorate, molar mass is given, and it's dissolved in a solution of 1.23 liters. What is the concentration of perchlorate ions in capital M, which is molarity? So what you have to remember is that the definition of molarity is moles per liter. So we're looking for the molarity of perchlorate. So we're looking for the moles of perchlorate, which is ClO4 minus, would be the formula of that anion, and molarity is per liters of solution. So we need these two quantities to find the molarity of perchlorate ions in the solution, and one of those is given directly. We're told that a solution has that much calcium chlorate with a volume of 1.23 liters, so that's going to be our denominator here, but we need to figure out how many moles of perchlorate we have to put that into the formula. All right, so first we need the formula of the compound to be able to think about how many perchlorate ions there would be. So calcium perchlorate is going to be, calcium is in the second column of the periodic table, so it's a 2 plus cation. Perchlorate, as we said, is ClO4 minus. And so when we cross those charges and make them subscripts, the formula for calcium perchlorate is calcium with 2 perchlorates. And that's going to be important because, again, what we're looking for is the total moles of perchlorate we have, not the moles of the whole compound in this case. So from there, we can do the series of steps that we need to find moles of perchlorate. This is similar to one of the first calculations we did on this, part of the test that deals with moles. I think it was back on number 6 or 7 on this test. So what we do is we start with the mass of calcium perchlorate. And then mass to moles, which is a very common conversion we've been doing several times already. So that's going to be 1 mole per, the given molar mass is 238.98. But again, we can't stop here because we're not looking for the molarity of calcium perchlorate. We're looking for the molarity of perchlorate individually as an ion. And if we look at the formula of calcium perchlorate, there's 2 perchlorate ions in the formula. It's CaClO4 2. So there's going to be 2 moles of perchlorate that release into the solution for every 1 mole of that compound that we dissolve. Because again, this is an ionic compound, so when we dissolve it in water, the ions completely separate. So when they separate from each other, for every mole of compound you dissolve, 2 moles of perchlorate are going to separate out into the solution. So that's the last step that's easy to forget, but we can't do that here if we want to get the correct molarity. So that comes out to 0.2147 moles. And so that's going to go up into here, into the numerator of this formula. So there's 0.2147 moles of perchlorate ions per 1.23 liters. So the molarity of that would be 0.175. And again, it's a numerical question, so just enter the number, not the unit. Okay, so again, this last step here is the one that we have to make sure we remember because we're looking for the total number of moles of that specific ion, not the moles of the whole compound in this case. All right, any questions on that? Okay, on to 14. All right, so number 14 here is if 125 milliliters of water is added to 225 milliliters of 0.254 molar NaCl, what is the final concentration in molar of NaCl? Assume volumes are additive and enter your answer with 3 decimal places. Okay, so this is what we should recognize as a classic dilution problem. Dilution is fairly simple mathematically and conceptually. You're just adding water to a solution and making it less concentrated, but it's sometimes hard to recognize when do I use that concept, when do I use that equation. So you use that when you're just talking about a single substance, in this case sodium chloride, and all you're doing is just changing the volume and the concentration of the solution. You're not reacting with anything, you're not changing it into anything else, it's just one substance, and we're just adding water to change the concentration. So recognizing that it is a molarity problem involving dilution, we can write this simple equation, M1V1 equals M2V2, and that's going to be what we're looking for. So we're told the initial molarity and volume, so we're starting with this molarity and this volume, so I'll call them N1 and V1, although which one you label as 1 and 2 is arbitrary. And then we're looking for the final concentration after we've added 125 milliliters of water. So we're looking for M2, the final molarity. All right, so 2 of those are directly given to us. M1, V1, as we said, are given, so that's going to be 0.254 molar, and V1 is 225 milliliters. Now we have to be a little bit careful here with V2 though, because in problems like this, V2 is not the amount of water that you add, it's the final volume of the solution after you've diluted it. So when we want to find V2, it's going to be the initial volume V1, which is 225, plus the amount of water that we add. We're assuming again that the volumes are additive, so we can just add them together. So 125 milliliters by itself is not V2, that's the amount that we're adding to the solution, so the final volume is going to be those 2 things combined, which is 350 milliliters. Okay, so that's going to be V2, and so that's going to be the number that goes into the denominator here when we're calculating M2 using this rearranged equation. So milliliters cancel out, they don't have to be in liters necessarily, they just have to be in the same unit. As long as they're both the same, they cancel, and then we're left in units of molarity, and that comes out to 0.163, capital M for molar, that'd be the number that you would enter there, 0.163. Okay, so that's going to be a typical dilution problem where we're using M1V1 equals M2V2. The volumes are the total volumes of the solution before and after dilution. And it's just recognizing it. So again, for problems like this, make sure that your answers are reasonable. So we're starting M1 equals 0.254 molar. We're adding more solvent to it, so that means the molarity should go down. So if your final answer was bigger than 0.254, that means you probably set up the equation wrong. So it's useful to always check your answers to make sure they're reasonable, and at least in this case it is smaller and it should be the right one. So that's how we would do it. Any question here? Yeah.
So I looked at a problem like this, a homework problem, and I'm not sure if it was exactly this layout, but it required for me to use the moles of the substance.
Yeah, so in problems like this, if you're going to use this equation, it's always in terms of molarity, not moles, but sometimes you might have to calculate the molarity first. So we might have a problem kind of like this where you kind of combine the two. We say you put this much compound into this much water, and then you dilute it to this volume. What's the final concentration? So for that, you'd have to calculate the molarity first before putting it into this equation. So sometimes it's not given to you directly like it was here. But whenever you're using this equation, it's not going to ever be in terms of moles, it's going to be in terms of molarity and volume.
Right.
Yeah. Other question?
How did you know that the V2 is 350 and not 125?
Because V2 is going to be the final volume of the solution after you've diluted it. So 125 is how much water we're adding, but we're adding that to the original volume, which is 225, so the total volume at the end is going to be the sum of those 2.
So that includes the water as well?
Yeah, because the 225 milliliters is mostly water. So when you have an aqueous solution, it's some amount of compound dissolved in water. So the vast majority of that volume is water. And we say we're assuming that the volumes are additive because when you add pure water to a solution, you're going to change the density, so technically it won't be exactly 350, but it'll be pretty darn close to that. And so if you assume they're additive, you just add the 2 together, and that's all there is to it. And we would never not assume that they're additive. There's no easy way to deal with that. All right, anything else? Okay, 15. All right, now we're dealing with reactions in aqueous solution. So the first of those categories would be precipitation, which is what we're dealing with here. And we want to know which of the following mixtures will not form a precipitate. So for these, we don't even necessarily need to balance the equations. I mean, we have to predict the products of these. So when you mix two ionic compounds together, you're going to swap the cation and the anion and form two new ionic compounds. Then you have to use solubility rules to figure out if one or both of those is insoluble. And we should know how to balance those equations, and they're not usually that difficult to balance. But for this problem, we don't really need to balance it. We just need to figure out what the products are and are any of them insoluble. So that's all we're going to do here. So in the first one, choice A, we have KCl and silver nitrate. So what we're going to do is we're going to swap the cations and the anions. So K is going to pair with NO3, potassium with nitrate, so it makes KNO3. And the other product is going to be Ag paired with Cl, silver chloride. Okay, so those are the two products, and we want to know if any of these are insoluble. So most silver salts are insoluble unless they're with nitrate or a couple other special exceptions. So that's going to be insoluble. So that one does form a precipitate. Remember, forming a precipitate means that there's something that's insoluble in there. For choice B, we're going to have ammonium is the cation for the first, pairing with perchlorate, which is the anion for the second. So it's going to be NH4ClO4. Ammonium plus 1, perchlorate minus 1. And then the other product is going to be Pb, which is lead, this kind 2 plus, paired with sulfate, which is SO4 2 minus, so it's going to be PbSO4. So silver and lead are sort of the two classic transition metal cations that almost always form insoluble products. So lead sulfate is one of the insoluble ones, and this would be soluble. All ammonium salts are soluble, all perchlorate salts are soluble, so that one's definitely soluble. For choice C, we have sodium carbonate and barium chloride. And then so what we're going to form is going to be sodium paired with chloride, which is the very common NaCl, salt, as we call it. And then the other one's going to be barium 2 plus with carbonate 2 minus, so the other product is BaCO3. And carbonate is one of the anions that is pretty much always insoluble unless it's paired with something like sodium or potassium or lithium and so on. So this would be insoluble. All right, and then finally for choice D, NaOH and iron chloride, sodium with chloride again, so NaCl forms again for that one, which we know is soluble. All sodium salts are soluble. And then the other product is going to be iron, which is 3 plus in this case because it's with 3 chlorides, and OH minus. So it's going to be iron hydroxide. Much like carbonate, hydroxide salts are usually insoluble except for the alkali metals and a few of the alkali earth metals, those first two categories. So if it's with a transition metal, hydroxides will be insoluble. So far they've all formed precipitates, so let's see if choice E does not, because there should be one of them that doesn't. So the products here are going to be calcium 2 plus with chloride, so calcium chloride. And the other one is going to be ammonium nitrate, NH4 plus with NO3 minus. All right, so this second product is a no-brainer. All ammonium salts are soluble, all nitrate salts are soluble. This one here, calcium chloride, is not the most obvious one, but most chloride salts are soluble unless they're with something like silver and lead and a couple other not as common exceptions. But this one, with all the group 1 and group 2 cations, so the alkalis or the alkali earth, like we have for sodium and so on, and calcium like we have here, those would be soluble chlorides. So these ones would be both soluble. All right, and so because both of those products are soluble in choice E, no precipitate would form, and this would be the correct answer to choose. So in every other case, one of those two products is going to be insoluble according to our solubility rules, which means it would precipitate out of the solution once we mix those two together. All right, so any questions on that? Yep.
What do you mean when you say salt?
Salt just means ionic compound. It's just a synonym for ionic compound. Yeah.
So when like the CO3 is like what element is there that makes it solid?
So carbonate is going to be soluble. So for the sort of always insoluble anions, which I believe are not carbonate and phosphate, they're only going to be soluble when they're paired with a group 1A cation, which would be the lithium, sodium, potassium, rubidium, cesium column on the first part of the periodic table, or they're going to be ammonium, which sort of behaves the same way. So any other carbonate or phosphate you would assume is insoluble. So those are the two anions that fall into the almost always insoluble category. Again, there's exceptions to that, and those ones that are always soluble, which are group 1A and ammonium, sort of take precedence in that case, but any other cation that these are paired with would make it insoluble. All right, anything else? All right, number 16. What are spectator ions when aqueous solutions of barium nitrate and sodium phosphate are mixed together? So for this, we need to figure out, again, we're mixing two ionic compounds, so we should think about the possibility of precipitation. And the spectator ions are going to be the ions that don't precipitate. So if you're doing a precipitation reaction, whatever ions stay in solution the whole time and don't combine to form a precipitate, those are going to be what you would classify as spectator ions. Now, some reactions don't have spectator ions, but most do. In this case, we're asked to identify them. All right, so what we're going to have is barium nitrate. So barium is 2+, as it's said in the answer choices. And then nitrate is going to be NO3-. So the first reactant is barium NO3 2. We don't necessarily have to balance the equation, but we will here just for completeness. And then sodium phosphate, so it's going to be sodium plus with phosphate, which is PO4 3-. And then the two products are going to be barium phosphate, which would have a formula of Ba3PO4 2. I think we might have seen that one earlier. And the other one is going to be sodium with nitrate, which is NaNO3. All right, so that's reactants and products. If we want to balance this thing, we need to put a 3 there. That gives 6 nitrates, so we're going to have a 6 there and a 2 there. So those are the coefficients. That's about as big as it gets for a precipitation reaction, a 3, a 2, and a 6. But again, the important thing in this problem is to identify precipitates so we can identify which ions would be spectators. So if we look at this again, as we just talked about, phosphate is pretty much always insoluble unless it's with sodium or lithium or something like that. So this is going to be a precipitate, but then sodium nitrate, both the cation and the anion are always soluble, so that's going to remain in solution AQ. Okay, so in problems like this, again, there's a few different ways of identifying the spectator ions. The short way is just to think, okay, which ions are not involved in forming the precipitate? Well, if we look at the product side of the reaction, probably can't read that because I ran out of room, but again, oh gosh, let me try to below it. NaNO3 is still labeled as AQ. It's a soluble ionic compound. So that means sodium and nitrate are not involved in forming the precipitate. The precipitate is barium and phosphate. So that quickly identifies sodium and nitrate as the spectator ions because they don't precipitate during this reaction. They're dissolved over here on the reactant side in the form of sodium phosphate and barium nitrate. And on the product side, they combine to form another soluble compound, so there's no precipitation involving those. That makes them the spectator ions. Now, the slightly longer way to go about doing this would be to write out the ionic equation and then figure out, again, which ions appear on both sides of the arrow. So if we did it that way, we'd separate the reactants into their ions, barium 2+, and then 6 NO3-, because there's 3 times 2. 6 Na plus 2 times 3, and 2 phosphates. So all the reactants are separated because they're all soluble ionic compounds. Then on the product side, we have one insoluble product, so that's going to remain as just barium phosphate. We don't separate something if it's insoluble. But then we also still have the 6 Na plus and the 6 NO3 minuses from the sodium nitrate. Okay, so then to identify spectator ions, those are going to be the ones that appear in the same form on both sides of the arrow. So we have 6 Na plus there, and we have 6 NO3- there and there. So then that again identifies them as spectator ions. They appear on both sides of the equation, dissolved as aqueous ions. And the net ionic would then be whatever's left over, which is just the barium and the phosphate combining to make the barium phosphate precipitate. Okay, so that's how we identify spectator ions, and then the final net ionic equation would be just to write it out in all its glory. You don't have to do all these steps as I said, because we're just looking for spectators here. Whatever is not a spectator ion remains in the net ionic equation. It's going to just be the ions that combine to form our precipitate. Okay, so those are the three forms of the equation, and however you want to do it, you can identify sodium plus NO3 minus as spectators. Okay, any questions? Yeah.
So whatever is not soluble, those are the ions that are spectator ions.
The spectator ions are the ones that are soluble on both sides. So we see that sodium is in a soluble ionic compound here with sodium phosphate. Nitrate is in a soluble ionic compound here with barium nitrate. And then on the product side, sodium and nitrate are paired together into a soluble ionic compound, sodium nitrate. So they're soluble on both sides, which makes them spectators.
So I meant to say whatever is not the precipitate, right?
So whatever is not the precipitate would be the spectator ions, yes. So in a precipitation reaction, whatever is not involved in forming the precipitate will be classified as a spectator ion. That's correct. Okay, we good? All right, and then the last one is a solution stoichiometry problem, or what is sometimes referred to as titration. So this is just a variation on stoichiometry. Like we did a few stoichiometry problems already that typically involved mass to mole conversions. Now when we're talking about solution stoichiometry, it's going to usually involve molarities and volumes as the units that allow us to determine moles of each substance. So that's the only slight difference. So we have a 2.34 gram sample of an unknown diprotic acid with 2 acidic hydrogens. So when we say that it has 2 acidic hydrogens, that means the general formula would be H2X. It's an acid with 2 hydrogens in the formula. When we say that there's diprotic, which means 2 acidic hydrogens, both of those tell us that. And it's neutralized with 0.375 molar NaOH. If it takes 40.9 milliliters of the solution to neutralize the acid, what is the molar mass of the unknown acid? So in a solution stoichiometry, or more specifically a titration problem like this one, what we're usually doing is we're using a known molarity and volume of one substance, NaOH, to find something out about the other substance that it's reacting with, which is usually also going to involve moles. So we know the molarity and the volume of one substance, we don't know something about the other substance, and we use that information to find it out. So when we're doing this, it's helpful to think about what are we looking for, first of all, because that's going to determine how we do the calculations and what steps we do. So we are looking for the molar mass of the unknown acid. So this is one variation on titration problems. We're looking for a molar mass. Molar mass, remember, is defined as grams per mole of substance. So to find the molar mass of H2X, we need the mass of H2X in grams, and we need the moles of H2X. All right, so that number is given to us. We know that we're using 2.34 grams of H2X, but we don't know right off the bat how many moles there are. And that's, again, in a titration problem, usually what you're going to have to find is the moles of the other substance that you don't know, okay? So we're looking for moles of H2X. We're going to use the information in the problem to do that. So once we identify what we're looking for, the rest of it is just a stoichiometry problem, where we have to write out a balanced equation and then set it up to do the proper conversions to find out the quantity we need. So the balanced equation for this is going to be an acid-base reaction. We should recognize that NaOH is a base, so it's going to be H2X, which is our acid, NaOH, which is our base. For titration problems, we don't need to worry too much about the product side. So let's first look at the reactant side, because that's the important part. So we have an acid with 2 acidic hydrogen atoms and a base that has 1 OH minus. So they need to react in a 1-to-1 ratio. So if we have 2 H pluses in our acid, we also need to have 2 OH minuses from the base. This only has 1 in the formula, so that puts a coefficient of 2 there. So that makes sure that we have 2 H pluses and 2 OH minuses. Those always have to react in the same amount. And so that's going to be the ratio that they react. That's the important part for this, because we're talking about relationship between the acid and the base that are reacting with each other. On the product side, we always make water and an ionic compound. So the ionic compound is going to be sodium with whatever X is. So it's going to be Na2X, because X would be a 2- anion in this case if it's a diprotic acid. Technically, there's going to be 2 waters forming because it's 2 OH minuses and 2 H pluses. So to balance that correctly, we need a 2 there. But again, we don't care too much about the product side for most of these types of titration problems. All right, so that's going to be the balanced equation, and then from there we can find what we're looking for, which is moles of H2X. All right, and as I said, the key difference in a solution stoichiometry problem is that we're not usually starting with a mass of a substance, we're usually starting with a molarity and a volume. So we have the mass of H2X, but we don't know its identity, so we can't use it in the stoichiometry, but what we have for NaOH is the volume and the molarity. So we know that we have 40.9 milliliters of NaOH solution, and we're going to use molarity as a conversion factor to go from volume into number of moles. So molarity is moles per liter or moles per 1,000 milliliters. So we want milliliters to cancel out, so that's going to go on the bottom. And the molarity is 0.375, so that tells us that we have 0.375 moles of sodium hydroxide per 1 liter, or more simply put for this problem, 1,000 milliliters allows us to do it in one step. All right, so that's the molarity of NaOH. So milliliters cancel out. And now that we have moles of one substance, we can find moles of the other by using stoichiometry. So we want to find moles of H2X. Now we want moles of NaOH to cancel. And from the reaction that we just balanced, there's going to be 1 mole of H2X for every 2 moles of NaOH that we add. They react in a 1-to-2 ratio. So that step is just the same as any other stoichiometry problem. And we stop there because all we're looking for is moles in this case. And so we go to 0.00767 moles of H2X. And then finally, to find the molar mass, we divide the mass by the number of moles. That's going to be that given mass divided by 0.00767 moles, which comes out to, well, 1 decimal place for this, so 305.1 grams per mole. All right, so in sort of solution stoichiometry or titration problems like this, there's a lot of variations. As I said, you could be looking for a molarity of a solution, as we did here. You could be looking for a molar mass. You could be looking for a volume of a solution, but it's all going to revolve around the same concept, where for one of those solutions, we're going to know the molarity and the volume, and we're going to use that information to find moles of that substance and relate it to moles of the other substance using the balance coefficients. All right, any questions on that? Yeah.
Can you please walk through the stoichiometry one more time?
Like how to get the balance equation, or how to do the calculation of the bottom?
The equation on the bottom.
Okay, so the way we do this at the bottom is, for solution stoichiometry, what you're usually going to do is you're going to, for one of the substances, you're going to know the volume and the molarity. So you're going to start with that because that allows you to find the moles of that substance. So for NaOH, we know that we have 40.9 milliliters, and we know that its molarity is 0.375 molar. So with 40.9 milliliters, we're going to use molarity as a conversion factor. Capital M means moles per liter, or more simply in this problem, moles per 1,000 milliliters. So we use that as a conversion to go from milliliters of solution into moles of NaOH. Once we have moles of NaOH, we use the coefficients from the balance equation to tell us that it's 1 mole of H2X for every 2 moles of NaOH. And that's how we go from there.
Thank you.
Yep. Other questions? There was one other hand up, but maybe it was already answered. All right, so now we're on to the home stretch, and as I warned you about in class, the people that put our test banks together, which I'm not heavily involved with, I just check it over. I don't really make the questions. They love redox chemistry, redox reactions. So there's going to be 3 questions on the exam that deal with redox. The first of those is going to be either just finding oxidation numbers or something more conceptual about redox equations, like back on the question. Okay, so then, the first question is going to deal with something, more conceptual with redox chemistry, and then we'll have to balance 2 equations as sort of the last 2 problems that we'll see. All right, so for number 18 here, we're just looking for in which of the following is the correct oxidation number for nitrogen given. All right, so we have 4 choices, and so we're just going to go through and find the oxidation numbers for all of these. So HNO3. So typically for oxidation numbers, we want to start with the elements that are fairly obvious and that follow simple rules. So hydrogen and oxygen are 2 of those. In pretty much every covalent compound, hydrogen is +1, oxygen is -2. There's very few exceptions to that. So we're going to have +1 for hydrogen and -2 for oxygen. And those need to add up to 0 because this is a neutral compound. So if we have 3 -2s and a +1, that's -5, which means that nitrogen needs to be +5 for those to add up to 0. So in this compound, HNO3, nitrogen should be +5. It's given in the answer choices as +4, so that one's incorrect. In B, it's a little bit simpler. It's NO2. Again, covalent compounds with rare exceptions, we're going to have -2 for oxygen. And then if it's -2, there's 2 of those is -4. Nitrogen has to be +4 so that those add up to 0. And so that one is going to be incorrect also. It should be +4, not +2. For choice C, NCl3, this one's a little bit of a trickier one, but for chlorine, it's going to be usually -1. So most of the halogens are going to be -1, especially if they're the outer atom in a formula, not the central atom. So it's going to usually be -1 for chlorine unless it's bonded to itself or bonded to oxygen. There are some exceptions. But for most things, it's going to be -1 for chlorine. And so if you have -1 for chlorine, 3 -1s is a -3. Nitrogen has to be +3 to balance that out to make them 0. And again, that one's going to be incorrect. It should be +3, not -3. And then finally for N2, any neutral element that's uncharged and has no other elements in the formula, so N2, O2, F2, whatever, that's the only situation where the oxidation number is 0. So N2 would have an oxidation number of 0, as any element would, not -1, so those are all incorrect. So as difficult as it is to stomach sometimes, you do have to pick none of the above for this answer choice. So all of those are wrong except for that one. Okay, so that's just assigning oxidation numbers, which is also an important part of the next two questions, so we'll need to do that. So any questions on this one or anything related? Yeah?
So, I want to ask, there was one question asking about what is reduction? What is true about we read off reaction, and it was and then the answer was just two answers. Reduction is a gain of electrons.
Yes.
And the other one says reduction is an increase in oxidation numbers or oxidation state.
Okay.
The latter is the correct answer. And I'm not sure why.
As you've stated it, the former of the two should be correct, unless you had them mixed up in your head. But basically, the concept there is not impossible if there's mistakes in homework questions, but the concept there is in a redox equation, so we're going to talk about redox equations in the next two, but just balancing them. It involves oxidation and reduction, both happening together. They always go together. Oxidation means that you're losing electrons, and the oxidation number is increasing. So when something is being oxidized or is undergoing oxidation, it's losing electrons, and that means its oxidation number gets more positive or bigger. For reduction, it's the opposite. Reduction is a process where something gains electrons, and the oxidation number is going to decrease, get more negative or smaller in overall magnitude. So like for these ones here, HNO3 is +5, NO2 is +4. So if you were converting HNO3 into NO2 as part of a reaction, it would be undergoing reduction because it's going from +5 to +4, and that means it's gaining an electron to do that. Okay, so that's what those mean, oxidation and reduction. So we learned that in class as Leo says Gur, the sort of way to memorize it. So lose electrons, oxidation, gain electrons, reduction. And then in terms of the oxidation number, they get bigger for oxidation, smaller for reduction. Does that make sense? Okay, any other questions? All right, the last two are balancing redox equations, which, as I warned you about many times, there are going to be two of these on the exam, so let's go through them. So when the following equation is balanced, what is the sum of all the coefficients? And again, anything that doesn't have a coefficient is going to be assumed to be 1. So I'm going to write this out again just so I have more room to operate. So H plus MnO4 minus NO, and then Mn2 plus NO2 and H2O. All right. So we have to assign all the oxidation numbers first. So for the ions that are by themselves, it's easy because it's equal to the charge. So hydrogen is +1 because it's just H plus. This is just going to be +2 because it's Mn2 plus. The rest we have to do a little bit of effort to get the oxidation numbers. So for MnO4 minus, again, oxygen is pretty much always -2, so it's going to be 4 minus 2s is -8. The total needs to be -1, so that means it's got to be +7 for manganese. +7 minus 8 is -1. NO is fairly simple because oxygen is -2 in covalent compounds. Nitrogen would have to be +2 for those to add up to 0. And then NO2 we saw in the last one, so it's going to be 2 minus 2s for oxygen, which leaves a +4 for nitrogen. H2O shows up in a lot of these as +1 and -2 every case. Can they not keep opening the door? That'd be sweet. All right, so we're going to have, those are all the oxidation numbers. And then when we balance the redox equation, what we start with is we find the reactants that are being oxidized and reduced, meaning that their oxidation number is changing between the reactants and the product side. We balance those first. So for manganese, it's going to go from +7 to +2. So that one is changing. And then nitrogen is going to go from +2 to +4. Okay, so those two are the ones that are changing. And the amount that they change by is equivalent to how many electrons are being lost or gained. For balancing, it doesn't really matter for us to know whether they're lost or gained, but manganese is going from +7 to +2, which means it's gaining electrons because the oxidation number is getting smaller, and it's gaining 5 electrons because the difference is 5, 7 to 2. And then for nitrogen, it's going from +2 to +4, so it's going to be losing electrons because it's getting bigger. One of them should gain, one of them should lose in all cases. But that's going to be a loss of 2 electrons because the difference in oxidation number is 2, going from 2 to 4. So we need to make sure the number of electrons are balanced, so we need to multiply one or both of these by a small whole number to make them the same as each other. So for 5 and 2, the smallest way to balance them is to multiply this by 2 to make it 10 electrons. Multiply that by 5 to also make it 10 electrons. So we need to multiply the coefficients by 2 for the ones that have manganese in them. So that's going to be a 2 and a 2. Then we need to multiply the coefficients by 5 for the ones that involve nitrogen. So we have a 5 there and a 5 there. So those are the coefficients that are now going to be set. But this one asks for the sum of all the coefficients. So we have to finish it off with H plus and water. So we're going to add water to make sure that oxygen is balanced first. So on the left side of the equation, we have 2 times 4 is 8, plus 5 is 13 oxygens. On the right side, we have 10 from NO2, so we need 3 more to balance it. So we're going to put a 3 in front of water. Now we have 13 oxygens on each side. And then we're going to use H plus to balance the hydrogen. So we have 6 hydrogens from water over here. Hydrogen only appears in this reactant, so we need a 6 there to make sure that there's 6 on both sides. So water and hydrogen get balanced last in most cases, water and H plus. And again, we're going to use water to balance oxygen, and then we'll use H plus to balance hydrogen last. So those are all the coefficients, and the sum is going to be 6 plus 2 plus 5 plus 2 plus 5 plus 3, which is 23, I believe. 12, 17, 19, no. 12, 17, 19. Am I not doing? Gosh, it's not multiplying, it's adding. I'm done today. All right. 8 plus 5 is 13, plus 2 is 15, plus 5, yeah, 23. I did it right. See, I'm not perfect. I thought I was wrong. All right, so that's how we balance that one. So questions on this one in the front, yeah.
So for H, if H didn't have a plus with it, would it be 0?
Yeah, but in that case, it would be in the form of H2. But yes, if it was just hydrogen by itself with no charge, it would be 0. Yeah, so if it is charged, then you have to account for the charge. And then the back? The oxidation numbers? Yeah, so those are going to be, there's a set of rules that we follow. So the ones I started with, which are the easy ones, are ones that are ions by themselves, just a single atom with a charge on it. In that case, the oxidation number equals the charge. So H plus has an oxidation number of +1. Mn2 plus has an oxidation number of +2. So those ones are straightforward. For the rest, we're going to follow the rules that we use for either compounds or polyatomic ions. So in almost every case, oxygen, when it's bonded to anything else except for oxygen, like H2O2, or except for like OF2, where it's bonded to fluorine. So with exception of those 2 rare exceptions, oxygen is going to be -2. So if in MnO4-, we have -2 for oxygen, and there's 4 of them, so that's -8. And then they need to add up to be -1, which is the overall charge. So if you have 4 -8s, you need to add 7 to that to get a charge of -1. So +7 would be the oxidation number for manganese. And then for NO, if oxygen is -2, nitrogen and oxygen have to add up to 0 in that case. So 2 and -2 would be 0, so that makes +2 for nitrogen. And then for NO2, we did that one in the last one, but reiterating it, oxygen will be -2 in covalent compounds. So 2 -2s is a -4. They need to add up to 0, so that means nitrogen has to be +4, so they add up to 0. So the sum of the oxidation numbers in anything that has more than one atom in the formula, the sum of the oxidation numbers equals the overall charge, which would be 0 if it's a neutral molecule like NO or NO2, or some non-zero number if it's a polyatomic ion like MnO4-. So definitely review that part of the notes if you're unclear, because that's going to be an important part of doing any of these balancing redox equations problems. Okay? Anything else? All right, let's just do the last one because it seems like there's a growing mob beating down our door that we need to get out of here for. All right, so this is a similar one. Now, there's going to be a small difference here, I believe, but it won't be, this one's not too bad, I think. All right, so we have these reactants and products. Again, we're going to assign oxidation numbers. So for ionic compounds, chromium chloride is an ionic compound. It's a metal and a nonmetal. In ionic compounds, the charges of the ions are equal to their oxidation number. So chlorine is in group 7, so as we know by now, it makes -1 anions. And that means the charge on the metal has to be +2 because you have 2 -1s. And so the charge on the metal is +2, which would also be its oxidation number. So for ionic compounds, the charge on the metal is equal to the oxidation number. HNO3 we did in the 2 problems ago, so I won't go through it again. It's +1, +5, and -2. And then on the product side, we have chromium nitrate, so another ionic compound. So if we have 3 nitrates in the formula, that's -1. 3 -1s is -3. In this case, the metal is +3. And then for NO3-, it's going to be, we treat each ion individually. -2 for oxygens is -6, and then we need to have a +5 for nitrogen again to balance that charge. And then HNO2, we have +1 for hydrogen, -2 for oxygen. 2 -2s is a -4, +1 is a -3. This has to be +3 to balance the charge. Water, +1, -2, no brainer. And then HCl, pretty easy because it's just going to be +1, -1. Hydrogen is always +1 in covalent compounds, and then chlorine is almost always -1, and those add up to 0. So those are oxidation numbers. Again, you have to become proficient at doing that to be able to start these problems. We look for the ones that are changing. So it's going to be +2 to +3 for chromium, which is 1 electron. And then we have +5. Sorry. Do you guys have the room?
Okay.
Okay, like 1 minute. Yeah, all right. I'm going to have to go through this quickly because we're out of time. But okay, so that's going to be 1 electron. That's going to be 2 electrons. And so we're going to need to double this. So we're going to have coefficients of 2 there and there. Now, what we also notice, though, is for nitrogen, we have some that's staying at +5. So we're going to have to add additional HNO3 to make sure that nitrogen is totally balanced. So when we get the coefficients, we get 2 CrCl2, and then we're going to get HNO3, but we're going to have to add additional HNO3 to balance. So we'll come to that at the end. And then on the product side, we get 2 chromium nitrates. So those have to be 2 because it's to balance the electrons. This has to be 1 to keep the electrons balanced. Then water and HCl. All right, and so what we need to make sure is we have the right number of nitrogen. So on the product side right now, we have this HNO2, which is 1 nitrogen. We have 6 more from the nitrates. 2 times 3 is 6. So we need a total of 7 HNO3s to balance the nitrogen. So one of those is involved in reducing to here. And then finally for water and HCl, I'll have to do this quickly. We're going to get, I think we just need 1 water in here because we have 21 oxygen. Yeah, we just lose 1 oxygen to make HNO2. So we just need 1 water to balance. And then for chloride, we have 4, so we need a 4 there. And then what is this asking for? What is the sum of the coefficients on the reactant side? So the sum would be 2 plus 7, which is 9. All right, so I'm going to wrap up because I feel bad taking the room from someone else that needs it. So if you have questions on this last one, just come find me outside. I'll separate out now, and I'll be in my office for at least a little bit until I have to take off. So you can come find me there as well. All right, thank you for coming. Sorry that it went long, and I will see you guys next week. And best of luck on the exam.